Thanks to everybody out there in the whole wild world. And it's really crazy times, but I hope you're all healthy and safe in your home offices or wherever you are. I would like to give you an overview style talk today on fuzzy and structure-driven navigation in billion-sized haystacks. The haystacks get bigger and bigger, but there were those good old times. And just the other day, I saw on Twitter one of those things where you eyebrow and think, yeah, that's actually true in a way. Dr. Bates, mask wearer, said, does anyone else remember the good old Sigma catalogs? Gosh, I love looking up chemicals in that. And perhaps those of you who were there already in the labs during those days, you may remember yourself sitting on the heatings and actually browsing through these wonderful books, some of which were really pieces of art. And Dr. Bates writes, I wish we could have Sigma catalogs again, with a smile or a whining smile, whatever that may be in the end there as an emoji. But then again, if we take a look back, so I checked a little bit the sizes of those databases that we grew up with, Maybridge in 2004, Cambridge 2004, and also these here, Sigma Aldrich, ChemDev. So here's the Sigma catalog. Since then, these libraries and databases of chemical compounds have massively grown. They have got bigger and bigger and bigger. With the advent of zinc, a new door has been kicked open. Our friends from Ottawa, the HTS catalog in 2020, the enumerated libraries, so one by one, merely takes off here from the zero line here, compared to what we now have accessible in front of us nowadays. Cambridge, Campbell, Aldrich Market Select, and Chem Navigator, for example, those are those where you can really order similarly as you did before, almost similarly as you did before from a catalog, but with much larger sizes. But then up there, there are fantasy molecules, and I mean this without any humor, but these are from Joy-Louis Raymond's group, the GDB generic database of compounds, where he and his team have enumerated compounds with a varying number of heavy atoms there, amounting to some crazy numbers here. But that's not it. It keeps on going further. So we reach now more or less the limits of molecular enumeration up here. So remember this, on the left-hand side, the y-axis is now a logarithmic axis. So what appears to be linear here is in reality an exponential growth. So here's GDB 11, just to take you up again where we left. Zinc 15, major step forward. Still all orderable by catalog, essentially. Ampule ultimate, and now we're touching the region where we get more and more tangible compound chemistry in there. So that means on-demand chemistry or virtual chemistry, what people sometimes call them. Still up here, GDB 17. So it already gives us a feeling that the chemical universe is even larger. We had those slides yesterday where we saw Regine Boacek quoted with her seminal paper on the estimation of chemicals, phase size amounted to well above 10 to the 60, so 63 and even higher. So definitely there we reach the limit where we can enumerate, count one by one those molecules in the databases. And now zinc 15 being the latest in the almost off-the-shelf purchasable compound collections here, and this being more and more hardly accessible as an enumerated database. Let's look at the associated costs in every respect. So enumeration, with an eye blinking, I call this how to blow the budget. Let's take a look. So I have sorted this table by use cases. So we have saving, storage of molecules, generating smiles, so expressions to actually store the molecules, then 2D similarity calculations, and so on and so forth. If we now take a closer look at what's actually happening here, you don't have to see and look at every little detail here. Let's just pick out a few. So for storage, Google have estimated 100 petabyte would be necessary to store a chemical space of size 10 to the 11th. And also, I haven't circled it because I was kind of hesitant to actually circle a figure like this. Google's estimate would be that they would have to have a payment of $1 million per year to actually have this storage space ready. But this column also here, CPUs or GPUs, I didn't differentiate here for simplicity reasons. The Confidant computation here that OpenEye did consumed 2,900 GPUs working there, and the associated cost for docking can well be a 6-digit figure, as it seems. That's an estimated or projected figure here, similarly to this 100 terabyte here, and not even to mention docking. And Argonne Labs have reported on a surrogate docking here, where not all the details have been disclosed, but we were talking about the 10 to the 12th sized chemical space. And they gave as a reference CPU hours, which is why I just put this in quotation marks here. So most of these numbers actually come from the NIH symposium on ultra-large databases that happened in December last year, which was very well attended and a super exciting symposium. Some figures here, OE means OpenEye, come from Christoph Grebner's webinar that we were happy to host. And our friend Wendy Warr is going to have a review published very soon, she said. And if you are not patient enough and want to see this right away, then please contact her directly. I put her Twitter hashtag in there, or Twitter, what's it called, handle in there. So these figures really blow the budget with respect to not only the numbers of CPUs, GPUs you need, and also memory, but also cost-wise and time-wise. So definitely that's not an easy task, and it's very obvious that we run against the wall in the not so far future if we continue to enumerate and just use faster and more horses. So that said, here is the famous quote that hopefully Henry Ford actually really said: if I had asked my customers what they wanted, they would have said a faster horse. So we need something radically new. We need something like a space car. And this space car should definitely scale well with haystack size. So it should not slow down considerably as the haystacks get larger. So it seems like we will have to exploit the combinatorics of chemistry behind. And the space car should still find the needle irrespective of how big the haystack actually is. So for this, we need a clever algorithm. We need clever brains. And good that we have some in our community. But it should ideally be affordable. It should not be expensive with respect to money and time and compute power run on standard hardware. And for this too, we need clever algorithms that deal with this challenge. So what's needed in this context? I think that's the obvious use cases for which we need the support, at the first level support. This is one of the typical drawing widgets that you see on compound makers, compound providers web pages, where you draw a compound, and after you've drawn your compound, you can choose between finding an exact match, finding a substructure, or searching for similar compounds in whatever database is behind or chemical space is behind. I stole this shamelessly here from our friends at ChemSpace, so Yuri, if you're in the audience, I will only talk very good about these things, so don't worry. Similarity. So I'm going to work myself up on this list here one by one. Let's start with similarity. We have feature trees, and in Infinicy, a tool that some of you may already be familiar with, a relatively new platform that we have, which is something that people obviously like very much. So what do these tools do? Essentially, the key is that we really need to capture the chemistry in the software. And I alluded to that already. The chemistry is exponential. So what do I mean by exponential? So let's take a look at this click chemistry example here. We have azides, we have alkynes, we have amines, and if we do click chemistry with them, we can arrive at a cyclization and connecting the amine with the acid into an amine bond formation. So what we essentially do is we give them linker atoms and denote these functional groups inside the software as something that can do something with something else, with another Lego brick. The Lego brick compatibility is certainly recorded. And once this has been done, then we can run over a building block or synthon lists, and we can check whether this is actually present. And we can transform this into, for example, a gray Lego brick. And then a Lego brick and a red Lego brick, for example, are defined to be able to undergo a reaction. So here we have 2 building blocks plus 2 building blocks plus 2 building blocks. If we do the chemistry, the obvious thing is going to happen. We get this combinatorial explosion. We get a 2 by 2 by 2 list of potential molecules, which makes 8 in these cases here. And you can easily imagine that if we do this with larger sizes of building blocks and more reactions, then we can easily arrive at zillions of molecules. So here's the chemistry know-how. That's the compatibility matrix, as we call it. So a green one can react with a blue one, a yellow one can react with a blue one, and a yellow one here can also react with a blue one. So obviously this matrix is symmetric. And the building blocks then contain these kind of colored Lego bricks that have the compatibility information in them. And then we combine this and run this over a reaction, have pre-processing software for this, and generate a chemical space. For those of you that are very interested in the details, the pre-processing software that we actually use here is called Colibri, and all the information on Colibri is on our website. So what then? Then we need a descriptor. We need something that describes molecules, and here comes something that parties the 20th anniversary, the idea of which parties its 20th anniversary. So it's really a great invention that Matthias and I came up with back in the days. So feature trees essentially collapse molecules into trees. That means since a tree is something that doesn't have cycles, that means that cyclic parts of molecules will collapse into one blob and so on and so forth. So we arrive at something that describes a molecule, but it's essentially coordinate free. Even though I put one onto each other here, and it seems like the feature tree knows about 3D, it does not. So the feature tree is a 0D tree style container for molecular information, and donors and acceptors, etc., encoded in these colors here. And what we then do is we do, for comparison of two molecules, we align feature trees onto each other and compute a similarity between those two. But how will this work when we actually operate in chemical space? Well, here's a query molecule, and there is a chemical space on the right-hand side, and it's full of fragments and the compatibility matrix, the compatibility rules there. And then we use something that some of you may be familiar with from protein alignment. It's called dynamic programming. It's a deterministic way of navigating through a matrix or hypercube of possibilities. And essentially what we do there is we transform the query into a feature tree, and now we cut it up into pieces, and from the chemical space, we take fragments that we align to the respective best fitting parts in the feature tree, obeying the chemistry, the compatibility matrix that I showed you before. We now build up one by one a new molecule, and we do this with a multitude of molecules. If you request 100,000 solutions from the chemical space, then this thing will be repeated, and the similarities will be monitored accordingly. And since the procedure is aware of its anamnesis, we know what molecule is behind, and we also know what question is behind. So there you go with your final result, and this is then delivered to the user. There are numerous application examples for feature trees, also for feature trees in fragment spaces already. Here's a recent one that Franka Klingler, Franka, if you're in the audience, thanks for contributing here to these slides. Actually, in the end, some of the ideas are from Franka, who has moved on to GSK now. But what we did here was we took a bunch, like a good dozen known actives, and this is in quotation marks here because they were merely active from this publication here, and asked a chemical space to deliver results here. And there were 5,000 similar results that we questioned or queried per input, and then we docked and scored those and visually inspected them, and a selection of 32 compounds came out that we liked. And in fact, all this cycle that arrived at 2-digit micromolar compounds here, so perhaps not super much if you think at first sight, but given the fact that these here were really merely active, and given the fact that this was really done in less than 6 weeks, we were very happy with this result. And we see this at various customer sites just as well, that this really speeds up things. Perhaps we can hear from Johnson & Johnson, from CJ, and perhaps also from Friedrich Rittmann, how things actually are able to accelerate the drug discovery process. There are certainly a couple of critical questions that always come up that we are confronted with. One of the most frequent ones is, don't you guys just increase the haystack? And why would you find more actives if you just increase the haystack? Well, if you compare this with fishing in a pond and doing this perhaps as a lonesome fisherman or fisherwoman, what's the likelihood to actually find many and diverse fish in this pond compared to something where they do deep sea fishing here with all its variety and diversity of the fish in there? So it should sound plausible that we actually find way more and way more diverse hits. And this seems to be true, and I can only give you a bunch of examples that our fellow clients actually reported on. And here is one that was also reported at the NIH Virtual Workshop on ultra-large databases last year. GSK, Jenny Elwood. Great talk, by the way. How did we do was on one slide, and Jenny showed a principal component analysis of the hits that they found. And in black, there is what they had found before. And in pink, these are all the new compounds that they found using the chemical space searching in their own chemical space. And you can see how nicely they actually spread out into more distant parts of the chemical space that is now spun up in 2 coordinates only here with the PC1 and PC2 coordinates. Another data point is Astrazeneca. So I mentioned before that Christoph Redner, who has moved on to Sanofi now these days, and when he was still with Astrazeneca in 2018, reported in our webinar series the number of hits increasing with the chemical space size. So here on that axis, you see the chemical space size, 10 to the 5th, 6, 7, up to the 10 to the 10th. And this is more or less a linear relation here. But look at this axis here, it's again a log plot. So this definitely increases rapidly with chemical space size. Another question that Uta Lessel thankfully referred and documented on, reported on yesterday already, is, do bigger and bigger spaces not simply overlap in the end? Well, chemical universe is so big that by now we are pretty certain that the overlap is really, really small. And here it is quantified. That's a Venn diagram that Uta showed yesterday just as well. And I was really surprised to see a single-digit figure here, low single-digit figure here. Namely, 3 molecules only were shared by subsets that were retrieved by showing queries in front of each of these spaces, because you can imagine that these are non-enumerable, so you cannot count up to 10 to the 12th anymore easily. So what was done there was you hold a query in front of this chemical space and ask, give me 10,000 solutions or 100,000 solutions, etc., back. And this was done with 100 queries here, so that roughly 1 million came out, and these were then compared, and only 3 were shared amongst all 3 chemical spaces here. So the details again are on Uta's slide from yesterday that we hope to be able to make available. But also this is detailed here in the ACS Meta-Analysis paper that she wrote up with Christian in 2019. Are the hits really different? Another question. And again, Jenny Elwood from GSK gave a very nice overview here. And we see on this slide here, it's regrettably very small. So it reads 0.82 here on the left-hand side, and it reads 0.98 up here. But these are bins essentially. So it says 0.98 up to 1. So that means that the higher we are here, or the more we are on the right-hand side, the higher the feature tree similarity. And here it goes roughly. And on the y-axis, we have the Tanimoto fingerprint similarity given to the query molecule that we have. It reads 0.4 here and goes up to 0.9. So interestingly, there are hits where we have high feature tree similarity, but relatively low Tanimoto similarity. And we also have hits where this is kind of mixed, low on both sides, and the obvious thing is if both say that's a high similarity, then usually it is a high similarity. But that's definitely, this part here should be something very interesting for people to look at, something where the chemists would not say that's an obvious chemistry, or that's an obvious similarity, sorry, because it's Tanimoto low, but feature trees say, yeah, but there is something which is similar with respect to the chemistry underneath. And then if we visualize these alignments that I mentioned before, chemists can really understand why two compounds are similar or not. So yes, the hits do differ from the old and other methods that people use throughout. There is also a Valenzuela et al. Paper from 2012, for example, where similar behavior has been observed. I put the reference down here. Okay, next in this list of use cases that we'd like to have support for is substructure finding. And thankfully, also, I didn't have to mention a lot, but this was kind of a first-time disclosure yesterday by Matthias Rahey in his talk. Matthias mentioned Haystacks, which is a new tool, brand new tool for substructure searching in large cases. The major brain behind this is Robert Schmidt, and Robert is currently writing up a manuscript. But the first steps have already been published here, namely those that correspond to the RIMAX library that Matthias mentioned before. I will not go into further detail here at this point, but rather refer you to the experts with this method, namely Robert and Matthias. And third in this is exact matching. And there, too, thankfully, Matthias's lab has done a lot of very nice work, 2-3 years, and have come up with SpaceLight. SpaceLight is published. Here is the glory for you to actually look it up. I call them future foreseeing fingerprints. So it's kind of those fingerprints that that can see their reaction fate in the future already. So how does this in principle work? Just very briefly here too. So similar to before, we have our click chemistry reaction here. So we do exactly the same thing in principle. We encode the chemistry, but then the methods will differ. Namely, the chemistry is not encoded in terms of a chemical space as such, but it's encoded in a topology graph. So per reaction, if you wish, we have a topology graph that describes what's going to happen from the left-hand side of the reaction to the right-hand side of the reaction. And then a partitioning is made for the query molecules, and you actually run over all possibilities in your fragmentation that comply with the compatibility graph. The method is guaranteed to find what is in the space, so there is no truncation or something of the space in that regard. It is fingerprint-like, so Lewis has looked at this, and it is indeed highly correlated with standard fingerprint ranking. Matthias showed this yesterday, I think. And it's also orthogonal. There is an enforced locality of the bit matches that are used in there. So it's very complementary to what we do in feature trees. It's certainly fast. It runs in seconds for the 17 billion real space that has been published in November 2020. So within seconds, really, you get an answer for the molecules that are fingerprint similar to your query. But beyond these use cases, are all our questions answered then, and are we happy? Well, not quite. It is also the chemical space side itself that is important, and I updated the graphics that we co-submitted to DDT as a graphical teaser here, and it has been taken up by a few of you from the audience and the speaker list already yesterday. Thank you for this. But what we see here is essentially there is now a set of commercial fragment spaces and chemical spaces that we use, notably these three here that we can very rapidly search using Infinity or Feature Trees FS. The latest kid on the block here is the Ottawa Cambria space that has been introduced yesterday in amine real space. Wushi's Galaxy or Galaxy. I'm alluding to the XY here at the end with the name. Zinc 20 certainly being one of the big ones amongst the group. But then there are also public spaces out here. We have come up with the knowledge space, which is a combination of public reactions with public building blocks amounting to 10 to the 14th. But if you look at this red constellation or arrangement of planets, pseudo-planets that I've tried to keep in size relative to the exponent here. So the radii scale linearly with the exponent here. So in this case, 26. That is currently the largest that I am aware of, GSK's XXL chemistry space, Merck's massive in 2018. Hopefully, and perhaps Friedrich Lippmann later this day is going to give us an update on the situation with Massiv.
Marcus, you have 10 minutes left.
Thank you so much, Alex. So all these spaces amount to crazy sizes by now, and so that's one problem that we have not yet talked about, and it's definitely being worked on. The other one is the 3D world. Yeah. So what is going to happen beyond just 2D molecular sketches? How about chemical space docking? And yes, we can now do docking of untruncated spaces. So any member of the chemical space in there can actually be hit. How does this work? Well, we use our chemical space. It's 10 to the sum molecules. It is, by definition, for example, a synthetically accessible chemical space, such as Enamine Real or Wushi's Galaxy or the Cambria space from Ottawa. And then we dock all the building blocks that are contained in there. That, as you may recall from the early slides, is just a small percentage of the 10 to the x. And then we certainly have filters here and there that check, for example, will I run against the wall? So here's my exit vector. I can hardly connect anything there. This will be ruled out. Or here, will I slam into the wall with a fragment that is already having a substituent there, and so on and so forth, and perhaps some survive. And then with the surviving ones being located at various positions in the pocket, of course, for example, maybe up there, maybe down there, then we continue our anchor and grow strategy, obeying to the compatibility matrix, and we build up. After visual and manual inspection, if you'd like to, we build up multiple complexes here. For example, this one survives, and then we can do a third round of filtering and come out with solutions that are synthetically accessible by definition, because at the very beginning we have put in the synthetically accessible chemical space as an input. So this has been performed a few times now in the framework of the service project and collaborations, and we recently started a new collaborative project with our partners from ChemSpace, from Enamine, from Crystals First, and from the Klebe Group at Marburg University, which is in the geometric center of Germany, actually, a very nice city. How does it work in principle? But Sergey will detail things there. So Sergey is next up here at the BioSolveIT Drug Space Symposium. Essentially, we exploit a fragment that already binds there as existing knowledge. And then with this existing knowledge, we do the chemical space docking. So we elaborate it in there. We mine, in this case, from Enamine Real, from the Enamine Real space, not to be mixed up with the Enamine Real database, which is an order of magnitude smaller. Synthesis was done, assays been done, co-crystallization and structure determination have been done. So rest, stay interested. Sergey will have exciting things to report on. So with this, I am approaching my last but one slide, the summary and availability of the things that I showed you. So today, the biggest chemical spaces that are out there can be searched exhaustively entirely using Infinici or F-Tree's technology. By exhaustively, I mean that we do not necessarily have to touch every molecule in there, but it's a non-truncating minor exceptions in the algorithms, I should say, procedure where every member of this chemical space can turn up as a solution in the end. We use substructure approaches, we use fingerprint-like approaches. These are currently being ported into our software platforms and software code base. These are currently being implemented. So I'm alluding to Spacelight and the Spacemax here. And for the docking, the same holds true. Any compound in that space can emerge as a hit. We explore the vast chemical spaces now with a 3D structure-based drug design, drug discovery. We come out with synthesizable, if we put in a synthetically driven chemical space in the beginning, we come out with synthesizable, directly purchasable or orderable compounds. This chemical space docking is no product yet. We are working hard on this to make this available so that you can do the computations yourself on your side. But BioSolveIT Discovery Service are certainly very, very happy to conduct such projects with you. With this, just a brief reminder, join the LinkedIn Chemical Space Club. We share updates. You can share your updates. There are early announcements, and we just stay in touch with each other during these hard days. So thanks very much for listening. It was a pleasure. Alex, I can see your face already, so the camera has been switched on. And yeah, that was it. Thank you so much.